For this final video, I wanted to provide a demonstration of how one might use MHDweb 2.0. This is going to be a pretty informal sample workflow, navigating between different tools, different mass runs and time ranges, and getting into the finer grained detail of what some of these tools can provide. I'm starting off this demonstration as a sort of a first-time user. If you've been using MHDweb and you have some plots that are active, you can always open a new incognito window or clear your cache. It'll effectively reset your session, and you'll sort of start off from ground zero. So to get started, I'm going to navigate to the Spacecraft mapping tool. In many ways, the entry point to a data visualization workflow is the time of interest. So by supplying a value in this field, you effectively filter the simulation database to return all runs whose run time range intersects with that value that you provided. For our purposes, I'm going to click this Key Events dropdown, which has some sort of important general solar events like Bastille Day, the Gannon solar storm, as well as some eclipses and Parker encounters. For our purposes, I'm going to select the total solar eclipse, which was in April of 2024. So by selecting this time of interest, the table on the right is going to display the mass runs that intersect with the total solar eclipse. So there's 15 distinct runs, which are quite varied in type. So we've got time-dependent runs, collection runs, steady-state runs. We also have some of our Carrington rotation runs down here. So we have a lot to work with. Another thing that I particularly like about this time of interest is that not only was there the total solar eclipse, but we also had a Parker encounter, Parker encounter 19, as well as some really interesting spacecraft interactivity between Solar Orbiter, Parker Solar Probe, Stereo A. So I think this will be a sort of a good test case for exploring the many tools that are on MHDweb 2.0. Now, suppose from here that I wanted to further refine my search query. Let's say for the Coronal model, I only wanted to take a look at our thermodynamic models, namely Thermo 2. I can go to this Models dropdown and select Thermo 2. Also, I just want to ensure that the runs that I'm viewing have the heliospheric domain, as there's certain runs that are in the database that only have a coronal domain. And so what we're left with here is these 10 mass runs. So to get us started, I'm going to take a look at this Parker collection run here for the Parker 19 encounter. This run itself is a collection of steady states that are sort of logically connected. Actually, you can see the individual steady states right above it. At each one of these timestamps, new data was ingested from the surface data source, which is adapt-gong, and sort of combined into this collection. So I'm going to select this and click Submit. Now the default spacecraft that is selected is OMNI, which is near-Earth plasma and magnetic field data. But since we're looking at a mass run that is specifically geared towards Parker Solar Probe and its Perihelion events, what we're going to do is collapse the tool menu, and from this drop-down menu in the observation widget, I'm going to select Parker. And as we can see, during that Perihelion encounter, you have that characteristic spiral right here. However, I think what I'm going to do is narrow the time range that I'm viewing, because by default we're looking at 7 days before the run start till 7 days after the run end. And so in these fields here, let's say I'm going to put in 2024, let's put in March 20th. And for the time range end, let's put in just a few days after the time of totality. So let's do April 11th. So now what we've effectively done is clipped that time range so that we're just looking at this Parker spiral here. So another thing that I want to do is underlay a magnetogram beneath the spacecraft mapping. So for the variable, I'm going to select the radial component of the magnetic field. And instead of a slice being at 15.5 solar radii, which is the midpoint of the radial scale, which spans between 1 solar radii and 30 solar radii for the coronal domain, I'm going to select 1. And so now we have a magnetogram beneath that Parker spiral. So this magnetogram looks a little bit oversaturated. So what I'm going to do is go to the color bar scaling drop down here in the view widget. Symmetric scaling is toggled on, and when no value is supplied here, we do is take the average value of the absolute value of the slice that you're viewing, and this works as a pretty good rule of thumb. However, sometimes it's going to be a little bit oversaturated, so instead of 2.51 Gauss solar radii squared, I'm going to put in, say, 10. And that should look a little bit better there. And since we're examining the view widget, the other thing I want to adjust is the actual quadrant of this longitude-latitude map that we're viewing, namely because the spiral in question is sort of centered between 0 and roughly 240 degrees longitude. So what I'm going to do is, in the x-axis, set this between 0 and 240. And for the y-axis, let's just change it to a little bit narrower band. So let's see, between -60 and 60 degrees latitude. There we go. So now that I've made some adjustments to the plot, one thing I like to do during a typical workflow is take snapshots as I'm moving throughout this sort of data exploration. And what I mean by that is, well, before I proceed, let me change the resolution of this image to a little bit higher. Instead of 200 dots per inch, I'll do 300. And then what you can do is simply click on the image, and it's going to open it up in another tab. And now, so I have this sort of snapshot of what I was doing during this workflow, and also allows me to really zoom into the image to get a sort of higher resolution, higher fidelity plot image. Now, alternatively, within the tool page, I can always click the download image option. However, I like the aforementioned approach because you can have a number of different tabs open in your current browser, and it makes it really easy to switch between the tabs to sort of compare and analyze fine-tune adjustments that you've made to the plots during your data exploration workflow. So just to illustrate what I'm talking about, currently we have this plot which is using the final state within this collection to trace field lines and to plot the magnetogram. So what I can do is branch this off into one tab. I can then select the state prior to that, branch that off into another tab. I can even do this a third time here. And now we have these three open tabs that are pretty easy to toggle between, and you can see these sometimes minute, sometimes pretty drastic changes in the field line tracing as well as the magnetogram. Or the other thing I can do is, let's say I select a single state here, and I have the Parker spacecraft mapping here, but I could also compare this to other spacecrafts during the same time range that we've selected there. So I could do solar orbiter, branch that off into a tab, do stereo ahead, and similarly branch that off into a tab, sort of compare the trajectory, the field lines that are being traced here between stereo head, solar orbiter, Parker. But with that being said, I'm going to return to the Parker mapping, and we'll explore some other options that we have available to us in the spacecraft mapping tool. So let's say I wanted to examine at a finer level of detail the spacecraft trajectory and how the particles are being ballistically mapped and ultimately traced back to the photosphere. So what I'm going to do is query by time, and the default time of interest that is used is the time range start. But let's say I wanted to use our time of interest, which is 416, which is the instantaneous time of this state. So let's put in 2024, 401. So now we have the specific spacecraft mapping for that particle at that time. Now, at this time of interest, Parker happened to be within the coronal boundary. It was at 29.7 solar radii. So there's actually no ballistic mapping here because this is sort of within the Parker encounter. But we do see where this particle maps back to the photosphere. Since I have the ephemeris of the particle at the photosphere, namely at latitude negative 10.8 degrees and longitude 220.4 degrees, I could query that point on the plot and see what the radial component of the magnetic field is by using the point widget over here. So I can toggle this drop down, and then I can use the information that is provided on the plot to supply the information for the queried position. So I'll use its longitude 220.4 and latitude negative 10.8. And you'll even see that the crosshair and point value on the plot itself move to align with where the particle mapped to the photosphere. But also what I'm going to do, just to provide a little bit more contrast for these crosshairs on the plot, is customize the style of the line color. And since it's over this sort of dark blue here, I think if I use white, it'll show up a little bit better on the plot itself. Also just keep this in mind that the spacecraft mapping is sort of an aggregate of different tools. You have the spacecraft mapping itself, but it is overlaid on top of sort of the radial slicing feature of Plot2D and the coronal hole map feature that you can find in the data products tool. So if I wanted to, I could keep this plot the same and open up those additional tools and sort of do the same process using the ephemeris that's provided here, query specific points within a given slice. So just to demonstrate this, say I go to the Plot2D tool. It's going to carry over with the same time of interest that I was just examining, as well as the variable that I was examining here. As you can see, the difference here is that by default it's slicing at the midpoint of the radial scale at 15.5 solar radii. So what I'm going to do is to query that position in three-dimensional space, I'm going to take the ephemeris from the spacecraft mapping plot. So we were at right at the photosphere here for the slice. I'm going to also scale the color bar so that it's symmetric around 10 Gauss, and if I'm not mistaken, let me just double check. Yep, we radially scaled it by r squared. I'm going to make sure that that is also toggled on. And now what I can do is query the position in terms of longitude and latitude. So we've got a longitude of 220.4, and if I'm not mistaken, it was negative 10.8. So now we have that same position queried that we were using in the spacecraft mapping, but from here we can also make certain manipulations without messing with the spacecraft mapping as well. So thus far we've only really examined radial slices, both in the spacecraft mapping and the Plot2D tool, but another thing that we could do is take a look at, let's say, a longitudinal slice. We can get a sort of side profile view of what's going on with the radial component of the magnetic field during the path of that field line that we were inspecting in the spacecraft mapping tool. So the path of that particle is starting off at 170.4 degrees longitude and ends up at 220.4 degrees longitude. So in our Plot2D tool, what we can do is select the longitudinal slice, and we'll start off at 170.4. And what I can do from here is I can step through these longitudinal slices, let's say at 10 solar radii increments. So let's go round that down. So starting from 170 degrees longitude, go to 180, 190. So now we can really examine each one of those slices to see what the structure of the magnetosphere is for this field line. And for the sake of demonstration, let's say I wanted to zoom in on this sort of inner coronal domain here, doing the same process, stepping through different longitudinal slices. I can go to the view widget, drop down this y-axis, which is controlling the radial dimension here. Let's say I just wanted to look at between 1 solar radii and 5 solar radii. And now I can return to 170 degrees longitude and step through that in 10 solar radii increments. So now I'm going to return to the spacecraft mapping tool. And we have this time of interest that's being queried for Parker, but we could also examine other spacecraft for that time of interest. So from this drop-down menu here, I could select Solar Orbiter or Stereo Ahead. Now, as you can see by toggling through those different spacecraft, although the spacecraft position is significantly different, the particle, the ballistic mapping for that particle, or in the case of Parker, the actual position of the spacecraft, all generally lie within this area here. So one thing I'd be interested in looking at is whether or not that particle is mapping back to the same coronal hole. So if I was to select from the data product drop-down menu coronal hole map, see that it's mapping to this open field line that has negative polarity. Go back to solar orbiter. You can see that we have 3 different spacecraft that are at different positions in terms of the coronal or heliosphere, but the particles that they're measuring at these positions are all mapping back to the same coronal hole. Another thing that I could examine for Parker's position in particular is that it's it's within the coronal domain, and it's in fact right over this open field line that has positive polarity, even though the particle itself, when tracing a field line, returns to this coronal hole over here. But I could provide a sort of cloud of points around that position to see if any of those map back to this other coronal hole here. So down here, I'm going to toggle on the point cloud option. And since we're at 29.7, I'm going to take a tenth of that. So let's do 2.97 solar radii is going to be the cloud sphere. So even within that that cloud of points, all of those positions are still mapping back to this coronal hole here. Now, even if I was to increase the sampling density of that cloud of points from 16 points to 32, or if I was to double the cloud radius, instead of 2.97 solar radii, I did 5.8 solar radii. All of these points are still mapping to this coronal hole, which is open field lines with negative polarity. Now, as I'm talking about this, I'm realizing that the position queried in this point widget here is indicating that the field line is closed for that photospheric position. I'm guessing that's because the actual position here is just right on the edge of the coronal hole. So I'm going to try just bumping this over by a small amount here, let's say 220.8 degrees longitude. And we can see that now reflects the open field line with negative polarity in this text up here. So another thing is that Parker Solar Probe has some white light imagers on its spacecraft. And so at this position here, we could go to the white light tool, and we can get a sense of what Parker is seeing at this specific ephemeris. So from the instrument drop-down menu here, I'm going to select Whisper 1. For Whisper 1 and Whisper 2, we default to the heliospheric domain because much of its trajectory, the view limits are actually viewing the heliospheric domain. But in this case, since we're actually within the coronal boundary, I'm going to select the coronal domain here. So on April 1st at 6 o'clock, Parker was exiting its perihelion. But what we could do is start before the perihelion and sort of step through in hourly increments to see the view of Whisper 1 as it's making that encounter. So I could go back just a few days to, let's say, do March 27th. Now, as I step forward a day, we'll see the sun get closer. So this green line is actually representing the inner radial boundary for the coronal solution of the simulation that we're viewing, but that is effectively going to be the sun. So let's say I was at 328 and move further into the encounter. So now we see it's getting much larger and now receding. So the point of sort of the closest point that Parker is reaching is somewhere right around here. So let's see if we can pinpoint more precisely where Parker is at the sort of apex of its perihelion. So March 30th at 6 o'clock, we're at 0.054 AU. Let's see if we go forward in time a little bit. It's okay, so it's moving away, so we're going to go back the other direction. 0.053 AU. 0.053 AU. And just to be sure, go to March 29th at 2300. And so now it is moving away again. So right at the beginning of March 30th is when it's at its closest point during the encounter. So now that we've fetched this ephemeris, let's say that instead of viewing Whisper 1, I wanted to extend sort of a similar view limit, but to go beyond this occulter that is built into the Whisper 1 instrument. So what I'm going to do is click on this image to branch it into a new tab, just so I have the ephemeris information for reference. And then return to our tool and click the custom view. And from here, I can input that ephemeris data along with the field of view to sort of mimic that Whisper 1 simulated brightness plot. All right, so we had a longitude of 94.55. We had a B angle of -3.74. And a radial distance of 0.053. So we've received this validation error over in the simulation widget. It says incorrect domain for current view. However, the default value for custom view is 0.53 degrees in line of sight. So what I want to do is actually adjust the axis limit so that it's sort of more faithful to the Whisper 1 view range. So the x-axis view limits are going to be between 13.5 and I think it's roughly 52 degrees. And the y-axis is going to be between -20 and 20. So if I was to return to that tab that we forked off earlier, I could compare these two plots here. See that the ephemeris is the same. The plot looks the same except for this occulter on the left-hand side. But effectively what that occulter is doing is going from that the lower bound on the x-axis limit, which was 13.5 degrees, to sun center. So if I go back to this tool, at the bottom here you have the option to show sun center. If I do that, we have a plot that is identical to the plot that we have over here. Now, as I mentioned earlier, the Whisper 1 instrument has a view range that is constrained between 13.5 and 52. I think it's actually 51.4, so let me adjust that. So it's constrained to this view, but what we can do in this custom view option is extend these limits, both in the x-axis and the y-axis direction. So let's say I wanted to shift this boundary into that occulter band here. Instead of 13.5, let's say I could go down to 10 degrees. Now we're looking a little bit closer to the sun. We can even put it down a few more degrees. So by shifting the lower bound of the x-axis, we're sort of uncovering a whole new layer of depth and complexity to this brightness plot as we approach the photosphere here. Now, on the other side of things, if you really want to just sort of mess around with different view angles, I could take, let's say we had 13.5 as the original thing. I could flip these, and let's say I wanted to take the maximum as -13.5 and the minimum as -52. So this would be looking at the other side of the sun here. And in similar fashion, I could step the upper bound of the x-axis range up towards the sun center, just as we were doing sort of the inverse on the other side. And lastly, what I could do is sort of combine the two plots, and so I could go from -52 to 52, so we're looking at both the left and right-hand side combined. Or alternatively, if I just wanted to have a symmetrical field of view, I could just put in 52 degrees here, and those two drop-downs will collapse. Now, since we're taking a look at white light plots, I think it might be beneficial to examine if within the Coronagraphs comparison page, if there's any viable data from Mauna Loa that we can use to examine this the same time of interest here. So I'm going to go ahead and select this tool. Okay, so that's great. So we have some coronagraphs that were taken from the Mauna Loa Observatory that we can use to do some comparisons for roughly this time of interest. As we can see here, originally we were taking a look at a time of interest of March 30th at 3 o'clock. The closest available coronagraph to this time of interest was March 30th at 21:33. Now, just as an aside, what's really exciting about this is that the Mauna Loa Solar Observatory has a fairly narrow data availability bandwidth. It's like a 4-year time range between 2018 and 2022. And actually the end date to that data range corresponds to the volcanic eruption of Mauna Loa, where the observatory is located. And it completely destroyed the access road up to the observatory. But during the time of the total solar eclipse in 2024, they, if I'm not mistaken, they helicoptered scientists and technicians up there to fetch these coronagraphs, which we can now use for comparison with our model results. So from here, we could mess around with some of the different vignetting functions. The default is the coronagraph one, but we could also select MHD. I could mess around with the radial power here and to hopefully highlight some of these streamers. But with that being said, I'm going to actually continue on and take a look at some EUV images for this time of interest. All right, so one thing you can see right off the bat is that this image is not scaled properly. Now there are some defaults that we apply to different filters. And so what should happen is if I select one of these filters here, say 193, it will toggle those defaults and we should get a more appropriately scaled EUV image. Now if I was to go back to AIA 171, we should see a there we go. That's a much clearer EUV image. So actually, if we go back to that spacecraft mapping tool that we were looking at, and currently we had Parker that we were examining, but let's say we wanted to take a look at Solar Orbiter here. So here we have the spacecraft position at March 30th at 3 o'clock. And what we can do is go back to that EUV page and examine what Solar Orbiter's FSI image is capturing at that time. So I'm going to return to the EUV page, and I'm going to select here Solar Orbiter FSI. We'll do 174 angstrom. Now actually, as I look at this, I realize that the Ephemeris doesn't look quite right. If I return to spacecraft mapping, I see, okay, so I have the time of interest, which is selecting which state to trace field lines with, but the actual time that I'm querying is down here, which is going to be April 1st at 6 o'clock. So let's align this with the time of interest. Let's do 3:30, 3 o'clock. All right, there we go. So now we have the correct ephemeris 173 longitude, -6.8 latitude. And let's go back to EUV. Yep, that looks right. Now, just like in the white light tool, I could use that ephemeris data to select custom view, put in the position of the spacecraft, and extend the view limits beyond what the instrument view limits are here. But for the sake of time, I'm going to move on. I'll leave that as an exercise for the user to explore. I'm going to go back to spacecraft mapping quickly. So one last thing that might be interesting to explore is time series data. We spent a lot of this demonstration looking at different spacecraft and how they interact with the model that we've selected. But we could also look at specifically at the positions and time during this model run range. How does the model compare to the instrument readings? So to do that, I'm going to go ahead and select the time series tool here. And we are presented with a validation error that says spacecraft positions do not intersect this domain. Now that is because you can see this sort of red highlight on the domain dropdown. It's because we've selected the coronal domain, but by default, as with spacecraft mapping, the spacecraft in question is OMNI, which is going to be near Earth plasma and magnetic field data. So first of all, I'm going to select, we're looking at Solar Orbiter, and I wanted to take a look at the heliospheric domain. And now another thing that I want to do is, by default, we're looking at the entire run time range, but if you remember, the beginning of this demonstration in the spacecraft mapping tool, I sort of constrained it just to the perihelion itself. So I'm just going to return to spacecraft mapping for reference here. And so our starting time range was 320, and our ending time range was 411. So I'm going to return to time series. And on the x-axis, or the time axis scale, put in 2024, 320. And the time range end, I'm going to put in 2024, 411. So in the spacecraft mapping tool, the starting point for each one of those particle mappings is measuring flow speed at the spacecraft itself. But what I can do with the time series tool is compare the in situ measurement with the model measurement at that position. So if I'm not mistaken, on the spacecraft mapping tool, we had aligned the queried time with the time of interest that's over here. So I'm going to query time in the time series comparisons with this drop down here and select 2024, let's see, 3:30 at 3 o'clock. And what we were looking to compare was the flow speed. So sort of the closest thing that we have to that would be the radial component of velocity here. And as we can see here, the model performed quite well at this time of interest. The simulated value would be 292 kilometers per second, and the spacecraft in situ measurement is 307 kilometers per second. Now, with that being said, we have done some data smoothing on the time series data using a boxcar averager, which I cover in the time series tutorial video. But if I wanted to get just the raw data, I could toggle this off. We can see the in situ measurement has changed to 300 kilometers per second. Now, just to quality check this value, if I return to the spacecraft mapping tool, we'll see that the flow speed measured by the spacecraft or by solar orbiter was in fact 300 kilometers per second. Now, the other thing that we could do is analyze how the model performed when compared to other spacecraft. So right now we're looking at solar orbiter. I could take a look at OMNI, which once again is the simulated measurement and the in situ measurement are quite close. And I can also take a look at stereo ahead. So it looks like during this time period for stereo ahead, we didn't have, there wasn't any available flow speed data. So on the spacecraft mapping tool, we were just using the approximated velocity of 400 kilometers per second. Let's see for Parker Solar Probe. Now the time of interest that we are inspecting is actually within the coronal domain. Previously we were looking at the heliospheric domain for the purposes of taking a look at OMNI solar orbiter. So I'm going to select the coronal domain. So unfortunately during the encounter, Parker doesn't have great plasma data availability. You can see though that when it's still within the heliospheric range, we have access to quite a bit of flow speed data. So actually the consequence of that for spacecraft mapping is that if we were to go back to that plot and we remove the time querying functionality, oh, let's see, I'm still selected solar orbiter, so let's select Parker. And we can see that much of this time range, we're actually getting the estimated flow speed, which you can see is defined by these magenta lines here, which indicates the mapping uses estimated flow speed of 400 kilometers per second. And so we sort of got a sense of that when we were looking at the time series plot, and there's this gap in data during the perihelion. So while there's not great plasma data availability for Parker during a perihelion, it does have good magnetic field data. So if I go back to time series and select the coronal domain and select the radial component of the magnetic field, we'll see that there is sort of an overlap here where there is Parker data for magnetic field and naturally the model data. So by default, the vector quantities of the magnetic field are shown as it's just the signed value sort of to determine the polarity of the magnetic field. But what I can do under Customize Style is toggle off the Show Sign Only. And by doing this, we can compare not just the polarity of the magnetic field, but how the in situ measurements compare to the model run. And since Parker has good magnetic field data for both during the apex of its perihelion and as it enters and exits that path. We can toggle between the two domains here. So we have coronal domain selected, but I can select the heliosphere, and we can see how the model compares to it as it's approaching the perihelion and within that encounter. Now, if you'll recall, the way that we came to this time of interest that we've been querying is when we were inspecting the WhisperOne plot in the white light tool. We were trying to determine where Parker had reached the apex of that perihelion. But in this point widget, I can also sort of toggle between the hours before and after that, just to see how the model and the in situ measurements compare when it's making that orbit around the sun. Now, throughout this demonstration, we've really constrained our analysis to a specific model run, but another sort of key part of this data analysis process is comparing different runs that intersect with a time of interest. So with that being said, I'm going to go to the simulation database and put in that time of interest. So we're looking at 2024, 3:30 at 3 o'clock. And so now we'll see a selection of runs. These are the should be the same runs that we were examining at the beginning of this demonstration. Now let's say instead of looking at the collection run, we wanted to take a look at just a sort of steady state Carrington rotation run. Let's use Thermo 2 for Carrington rotation 2282. So just for comparison's sake, the run that we were just looking at used the adapt gong as its sort of data source for generating that boundary condition. For our Carrington runs, we're using HMI as the sort of empirical data source. So just to better compare those, I'm going to branch this into a new tab. Go back and take a look at the Parker run for P19. And then branch that off into a new tab. So now what we can do is go between these two tabs and sort of see how these two models compare during that time period. So although the surface data source are different between HMI and adapt gong for the perihelion run, they both use the thermodynamic model, namely Thermo 2. But let's say we wanted to compare the thermodynamic model to a wave turbulence driven model. Go back to the simulation database. Let's see, our time of interest was 2024, March 30th at 3 o'clock. Let's say I select the Eclipse 2024 Live, which is a time-dependent run, and the Coronal model is the WTD, or the wave turbulence-driven model. So I'm going to select that. And now, this time series is going to take significantly longer than the other one. The other ones were steady state or a collection of steady states. This is hundreds of distinct states at an hourly cadence. So the time to generate that time series wasn't terribly long. It's because we're only interpolating the states that intersect with the coronal domain. Currently for the Eclipse 2024 time-dependent run, we only have the coronal domain accessible on the simulation database, but in future iterations of MHDweb 2.0, we'll include the heliospheric run for that as well. Now, for the sake of comparison, I can branch this into a new tab, and I can compare the WTD model with the two Thermo 2 models that we were examining before. So I'm going to go ahead and return to the simulation database, and I'm going to select, let's just do a Carrington run here. I'll do Carrington rotation 2282, Thermo 2. Oh, and just on a side note, you may have noticed that when we were comparing these plots, that the time range for the Thermo 2 was slightly off from the other two models. So those sort of peaks and valleys line up in a similar position. But for the Carrington run, it's slightly off. That's because this Carrington rotation 2282 goes to April 8th, whereas these ones go all the way to 413. If I'm not mistaken, the time range that we'd specified in this view widget here was between 320 and 411. since the Carrington run doesn't go all the way to 411. As you can see, it says value out of bounds, so it's going to clip the upper range to the run max time range. Now, using this Carrington rotation run, I'm going to return to the spacecraft mapping tool. Now I'm going to make a few adjustments to this plot. I'm going to remove the queried position. I'm also going to remove the text in the upper left-hand corner. Since we're looking at a coronal hole map, we don't really necessarily need that. I'm going to remove that. Now that I have this plot the way that I want, and let's say I want to share it with colleagues or reference it later, I can click the download image button here. But let's say I wanted to analyze the underlying data for the spacecraft mapping in sort of finer detail. I have two options you'll find to the left of the download image button, namely download .ecsv and download a .dat file. So this first option here is going to return data that is structured similar to the ASCII data that is downloadable in MHDweb 1.0. But the .ecsv file is particularly useful if you're exploring this data in a Python environment. As I mentioned in the time series and spacecraft mapping tutorial, as both of these offer data downloads for .ecsv files, this file format stands for Enhanced Character Separated Values, and it was created by the developers of astropy. It's sort of a human-readable file format which can be read into a Python script to produce an astropy table. So it's similar to a CSV file, but provides additional metadata about the data contained in the file. And when read in using astropy, will yield a table with native Python data types, relevant units, coordinate systems, and timescales. So although this demonstration is by no means any sort of comprehensive look at how to use astropy, it's a really wonderful package, and I highly recommend looking at the documentation link that I'll provide in the video description below. But just to sort of get started on how you might accomplish this, let's go ahead and click on this to download the table. Now what you can do is in a script or a Jupyter notebook, for these purposes I'm just going to open a terminal. You can read in this file path as an astropy table. So using whatever Python package manager of your choosing, I'm using Miniconda. And I have an environment here that is really just Python and astropy, sort of a bare bones environment. And I'm going to enter my interactive terminal. And from here, from the table module, I'm going to import the table class. To create the astropy table itself, you do table.read and then pass in the file path that you downloaded from MHDweb 2.0. So you get some data type warnings. This is for the various timestamps for the spacecraft, the coronal position, and the photospheric position. These are all supplied in numpy's datetime 64, although these can be cast as strings or even as astropy's time objects. So from here, if I just want to view the table in and of itself, I can just print that out here. We can see a variety of different columns, and this is corresponding to that spacecraft mapping plot that we were viewing earlier. If you want to view what columns are available to you in this table, you can simply say table dot, I think it's columns if I'm not mistaken. You'll get a list of the string values for the column names. Also, the table itself has a sort of a metadata dictionary as well. So if you say table.meta and you supply the keys there, you can see sort of what values are contained within this metadata dictionary, or you can also just print that out as well. And you'll see the spacecraft that you're looking at, the name of the mass run that you're viewing, what domain it's within, and the queried time range, among many other things. Now the table itself is accessed very similar to a named array in NumPy. So what you can do is specify the column identifier, which we printed out up here using table.columns. So let's say I wanted to take a look at, say, the radial position at R1. and this will supply us just that single column. So as you can see here, it supplied the column identifier, the Python data type that is being used, as well as the astropy units, which is another really wonderful module that astropy supplies. It's in solar radii, and there are 528 entries. And as you might expect, for the coronal boundary, the radial position for the particle as it's ballistically mapped back is going to be 30 solar radii. But let's say, let's take a look at the column names again. So let's say we wanted to take a look at what the radial position of the spacecraft was. Say table, it's going to be spacecraft position R. And now what we're going to be provided with is a column that is displaying the radial positions of the spacecraft at the queried times. Now from here, using the Python package of your choosing, you can explore other meaningful observations from this table. Let's say you wanted to take a look at just the times where the spacecraft position was below, let's say 85 solar radii. So what you might do is say table at, I think it's spacecraft time, and I only want to take a look when the spacecraft position in the radial dimension is less than 85 degrees or 85 solar radii. So now we have, this returns a column. The length of the column is less than the original length, as you'd expect. Now it's 487. And so this is going to correspond to the masking or the filtering that we've done in this last command. So with that being said, I'm going to exit this interactive session and return to our spacecraft mapping plot on MHDweb 2.0. Now with that being said, I think that just about wraps up this demonstration of Predictive Science's new MHDweb. As I've mentioned before, this website is still under very active development, and as we add new tools and new features, we'll provide additional resources and tutorials to sort of cover those elements that are entering into the website. Hopefully this demonstration has been useful, gives you a sense of how to navigate between tools and flesh out this time of interest. I know we're going on an hour here and we haven't even explored the applications of Plot 1D or EUV comparisons. So if you have any questions regarding this demonstration, or there's something that's not fully clarified in one of the other tutorial videos within the series, please just leave a comment below. In any case, I hope you enjoy exploring solar phenomenon and simulation and model results with this new MHDweb 2.0. And thank you so much for watching.